Hello, welcome to this VIb Tip session. Today we are covering octaves and decibels, fundamental concepts on vibration units management. These are applicable to any type of vibration, but for instance we can often hear about a sine profile slope of 12 dB per octave or increase the PSD level 3 dB for a random test. When we receive a profile from a standard, we can get grabs at these two examples of a sine and a random profile. In the horizontal axis, we always have frequency, and in the vertical axis, we can see the corresponding unit, Gs in sine, or G squared per hertz in random. First thing we realize is that axis values are not equi-space, and we have similar axis distances between 5 and 40 Hz than between 200 and 1600 Hz. We also see that in the vertical axis, the figure seems to be increasing in factors of 10. Why is this happening? Well, the magnitudes we find in vibration and shock can vary over a huge dynamic range. We should be able to plot small values together with large values in the same graph, like for instance 1 Hz and 2000 Hz or 0.0 G and 100 Gs. Linear scale doesn't allow us to do that, so we use logarithmic scale. For both axes we use these logarithmic scales, and therefore the graph type is so-called bi-logarithmic. Here we have a frequency linear scale from 1 to 64 Hz with intermediate frequency values twice the previous. Whenever we multiply by 2 a frequency, we say that we increase 1 octave. We have 1 octave between 1 and 2 Hz and the same 1 octave from 1000 to 2000 Hz. If we apply the logarithm in base 10 of those frequencies, we get figures of 0.3, 0.6, etc. They are equi-spaced by a factor of 0.3. and therefore we have the same axis distance between frequencies separated 1 octave, and consequently generating a logarithmic scale. The number of octaves between two frequencies can be calculated by the simple formulation shown below. We do something similar in the vertical axis. In this case, we consider acceleration in Gs and apply the logarithm in base 10 using a reference value that we choose at our convenience, in the example 16 Gs. The result of the logarithm is multiplied by a factor of 20 to reach the corresponding dB figures. We can see that when the acceleration level is reduced by half, we decrease 6 dB. It's important to understand that in vibration testing, we don't consider a fixed reference value for calculating the dBs, as we normally do in other techniques like acoustics. We can choose any figure as reference, since we will always be talking about dBs between two levels. It's also important to consider that the previous factor of 20 and therefore plus 6 dB when we multiply the figure by 2 or minus 6 dB when we divide by 2 must be applied to basic magnitudes as acceleration, velocity or displacement. Nevertheless, if we are working with power or energy related magnitudes like power spectral density, the applicable factor is 10 and consequently the rate becomes plus minus 3 dB per octave. So, summarizing, here we have the dBs increase or decrease depending on the increase-decrease in the magnitude when it is multiplied by a factor of 2 or by a factor of 10, and the formulas to calculate it. Well, that's all for now. Thanks for joining me in this session and see you in the next VIb Tip.